This Week in Virology, the podcast about viruses, the kind that make you sick. From Microbe TV, this is TWiV, This Week in Virology, episode 832, recorded on November 19th, 2021. I'm Vincent Racaniello, and you're listening to the podcast all about viruses. Joining me today from Fort Lee, New Jersey, Dixon Despommier.
Hello, Vincent and everybody else. Out the window, there are puffy little white clouds. It's a little breezy and it's a little cool. It's in the 40s. I guess the humidity is at an appropriate level for being in the 40s in November. And it's the week before Thanksgiving.
You've been well, Dixon? Haven't heard from you in a while.
Yeah, I've actually surprisingly well. So things are moving along, as they would say.
Glad to hear it. Also joining us from Austin, Texas, Rich Condit.
Hi there. 65 degrees, sunny. It's a beautiful day.
Good deal.
It's the same here as it is for Dixon. It is 8 degrees and sunny. Actually, it was like in the 70s yesterday, Fahrenheit anyway.
Bizarre day yesterday.
Bizarre.
That's right.
And then this morning it dropped. Also joining us today from New York, Amy Rosenfeld.
Hello. I didn't see the puffy white clouds. My clouds are gray.
You're gray, yeah.
Well, there's some gray here too.
Amy is up at Columbia University today.
I'm always at Columbia.
Action Central.
It's true, you are always at. Although last night you were at the incubator, right?
I was,
Cool.
but I spent the day at Columbia.
So let's see, you're 168th and I'm at 30th, so that's 130 blocks, which is like
About 7 miles.
7 miles, 20 miles per block, yeah.
20 blocks per mile.
Yeah, sorry. 20 blocks per mile. That's absolutely right. Just a reminder, everyone, throughout November, December, and January, all of your donations, which you could make to parasiteswithoutborders.com, will be matched by Parasites Without Borders and donated to Microbe TV. So parasiteswithoutborders.com, you can click the button, and your donations are tax deductible because they are a nonprofit, as we now are. Microbe TV is now an IRS-approved 501c3. So any of you making donations to us via Patreon or PayPal, it's tax-free. Now, Daniel is matching donations up to $40,000 total, right? I don't know how that works. So if people give up to 20, he will match it, and that's 40, and that's it. But if you want to give more, if you say want to give $500,000 to us, you can go to Microbe TV.
No, you don't.
Nobody's going to stop you.
You go to the Rosenfeld Racaniello laugh at Columbia, and then
That's true. You can do that.
donate to Microbe TV.
The Grand Cayman Island Bank, care of.
Exactly.
As a nonprofit, we can now donate to other nonprofits of our choice. Just as Parasites Without Borders, they'll do campaigns for Doctors Without Borders and floating hospitals and so forth. So
That's right.
I think that's a requirement for a nonprofit to only donate to nonprofits. You can't donate to a for-profit because that's sending the money back into the tax stream or whatever. I don't know.
Correct.
What do I know? All right.
You know a lot.
We have a very exciting lineup for you today, starting with a story I thought Rich Condit would like. I don't know if you heard about this, Rich. But
yeah, I've been following this. And
all right, so tell us what's going on.
Earlier this week, a lab worker cleaning out a freezer at an old Merck facility in Pennsylvania found 15 vials with 5 of which were labeled smallpox, which is a little scary, and 10 of which were labeled vaccinia being the virus that was used to vaccinate against smallpox. Okay. So, I think it's actually a good story. They did all the right stuff. They called the CDC. CDC sent their SWAT team and securely gathered up the samples and secured the facility, transported the samples to CDC in Atlanta, where they have a BSL-4 facility that's perfectly qualified to, and workers perfectly qualified to deal with all this, and examined the contents of those vials. And it turned out that the vials that were labeled smallpox did not, in fact, have the smallpox virus or variola in them, but rather had vaccinia, the vaccine strain. So they are all, in essence, harmless vaccinia. Actually, my guess is they just did sequencing on these and didn't try and grow any virus out of it. Okay, end of story from the point of view of the public, I think. But I want to see more, dude. I want to know if you can grow virus out of these. All right, and I also want to know what it is they're calling vaccinia, because as we may discuss some episodes in the future and have discussed in the past, the origins of the virus that we call vaccinia are somewhat obscure, and different manufacturers used viruses apparently from different sources. Okay, and so it would be interesting to find out what the full history is of this stuff and what's actually in those vials. But at any rate, I think it's actually, in a way, well, I suppose a good news, bad news story, because the only remaining supplies of stocks of smallpox are supposed to, or variola virus, the virus that causes smallpox, are supposed to be in Atlanta and in Moscow. Okay. And as far as we know, that is the case. But there's always been in the back of people's minds, since there was a time when smallpox virus was worked on in a number of different laboratories, even though investigators were told to destroy and or transport their stocks to CDC. There's always been the suspicion that, did we get everything? And so I suppose the bad news here is that, here's an example where it's, you would think that somebody cleaning up, if they saw smallpox, something labeled smallpox, would have gotten rid of it. Okay. But it exists. But the good news is that they did all the right thing in response to it, and it turns out not to be smallpox. And even if it were smallpox, they did everything so well that nobody would have been harmed.
So first of all, someone mislabeled a vial. That's weird that they would label it smallpox. I wonder how long ago that was. It must have been before eradication, right?
Yeah, I suppose.
The other is, so let's imagine what they did at CDC. They probably put these into the BSL-4 and then added whatever, trizol or whatever, to inactivate and extract the nucleic acid and then pass it back out for sequencing, I guess, right?
Yeah, I wouldn't want to do that. I would want to put in some buffer, because I want to know if there's live virus there, out of curiosity. Okay.
Sure.
Okay. So I would put in some buffer. Okay. And carefully withdraw some of the resuspended preparation, put that in trizol to inactivate it, and store the rest away securely for future studies. But the first thing you want to do is sequence, because I'm sure that's going to be the quickest and safest way to find out what's actually in there.
And the sequencing might tell you where the vaccinia came from, right?
Yeah. At least, it might. Okay. There are, like I said, the lineages of vaccinia are confusing. Okay.
Right.
So that's why I want to know what it is. So it ought to go on the historical / phylogenetic tree of vaccinias to see if we can figure out what Merck was working with. And as you already pointed out, we don't know when this was. I don't know if there's a date on it. I don't know if anybody can trace exactly when these were in use or when they were put away. So.
And you remember a number of years ago, they discovered some vials at NIH, right? That said smallpox on them also, right?
Yeah.
And they were actually not vaccinia, I think.
I forget the whole story on that.
Yeah, they were cleaning out an old freezer.
Yeah, I don't. I'm not sure they actually said smallpox on them, but there was some suspicion that they could have been, given the circumstances. Yeah. And I don't think it turned out to be smallpox, but I don't remember the details. I do remember a flap. But
what's the original source of vaccinia? Is that goes back to cowpox, or?
Well, that's the interesting thing. Okay, if you follow strictly the Jenner story,
Yes.
The very original strain comes from the hand of a milkmaid,
Right.
Who had cowpox that she picked up from milking a cow.
Right.
But there were probably historically numerous repeated isolates with time, and there's also suggestion in the Jenner literature itself that some of this virus may have been through horses.
Horses,
at
yes,
some
I
point.
recall that too. Yes, indeed.
And there's some evidence from some of the sequencing that's been done that some of the things that we call smallpox are in fact mostly, if not exclusively, horsepox, though not all of them are. Okay,
Horsepox,
so there are probably numerous different isolations of stuff that was used as smallpox vaccine. Stuff was passaged under a variety of different conditions. And so I would say that what we call vaccinia is, in a global sense, heterogeneous at best.
Right.
And people are trying to sort this out. One of the greatest stories that we covered some time ago is, there are a couple of groups that are looking into this, for history, if nothing else, to find out who was using what, when, and where they got it. Okay. And it's a complicated story, and there's been a lot written about it. But one of the samples that was analyzed, one of the investigators got, believe it or not, on eBay. Okay.
Yeah, I remember that.
Somebody was selling some old vials of smallpox vaccine on eBay.
That's crazy.
And it's there's pictures of the vial and everything in the paper. And they actually managed. I don't recall whether they actually got virus out of that or not, but they got sequence out of it.
That is crazy.
Okay? But people are, getting virus from museums. There's museum samples where they have, displays on what smallpox was and how it was eradicated and stuff. And occasionally, you'll run across one where there'll be some old vial of smallpox vaccine. So that's a source of sequence that you could get to try and answer the very question you asked, Dixon.
Maybe they just forgot to put the word vaccine on the same vial on the one that they found at CDC.
Yeah, that could be. That's a good point.
What is pretty clear is that none of these things are what we today recognize as cowpox.
Right.
Okay.
Right.
They're definitely different than that. And a lot of the virus that we call vaccinia has no, there are no naturally occurring samples of it now. The only occurrences of the virus that typically is called vaccinia in nature are spillback. Okay. That is a virus that's gotten back into cattle, into agriculture via vaccination of humans.
Interesting.
Yeah.
Right. All right. Now we have a trio of papers for you. And the first from Eurosurveillance, re-emergence of enterovirus D68 in Europe after easing the COVID-19 lockdown, September 2021, from a huge cast of individuals, and you'll see why. But the last author is Heli Harvala, and who was on a TWiV in Copenhagen a couple of years ago, along with Thea Fischer, who's also on this paper, and many, many other people. And this is right up Amy's alley. So perfect, Amy. What's going on here?
Well, it's the first sighting of EV68.
Since like 2018 or?
Yeah, pretty much. Well, there was one case of 68 in the United States in 2019 before the pandemic really.
So give us the executive summary of 68 and
the executive summary of 68 was
the background that we need to understand this. Yeah.
So it's a respiratory disease, and it cycles, at least here and in Europe, basically every other year. So on even years, there are outbreaks that associate with the development of childhood paralysis, or AFM. And it follows the predominant enterovirus seasonality, like late summer, early fall, and hits young kids. And then we don't see it for the odd years. And so in 2020, we were expecting a big outbreak because since 2014, every outbreak that has occurred has been larger and larger. But when we all stayed home and wore masks and physically distanced, there was no outbreak of 68. But you saw a huge reduction in almost every respiratory disease out there, from RSV to influenza to some of the bacteria and everything. But enteros, they decreased, but they did not really decrease as significantly to zero as like RSV and others did, because there's a lot more of them out there. But when people eased up on their restrictions, RSV and a lot of the other respiratory viruses came back with a vengeance, and that's because, or what we think is because, you now had a larger naive population, and also it moved the seasonality of the viruses slightly. So RSV is normally winter, and it started to be seen in late summer, or like late spring into the summer, and it's still continuing today. But in that population, when you looked at enteros, you didn't see any entero 68 if you assayed specifically for entero 68, because the commercial panel just assays for entero/rhinos. So the question has always been, where is 68? And so this is the first sighting of 68 coming back from vacation, I guess. So there was 139 cases in September in Europe, mostly in September, late August, following the traditional entero seasonality, hitting the right population of kids, basically, children under 17. But there was no AFM. So none of these children had what is classically called acute flaccid myelitis. They didn't fit the criteria. I think 5 of them had some kind of neurological complication. And so this is different than what we're seeing in the United States. So in the United States, we haven't seen any AFM any 68 since that one case in 2019. And we've also really only seen 2 or 3 cases of entero-associated AFM, and they were with 71 and Echo 11, and then potentially with a rhinovirus. Not really clear about that association. So now it's just a call of it's just since they're all passively surveyed, which means that it's dependent upon the local health department reporting it. It's a call of action to make sure that you start to report when you start to see the increase in rhinovirus/enteroviruses, and you start to look out for children who will have some kind of neurological complications.
So
Amy,
most of
any
these.
thoughts on? I'm sorry. Go ahead.
Okay, go ahead.
I just wondered if Amy had any thoughts on where that might have arisen from to start a new epidemic.
So I think it is always constantly circulating. I think it's just beneath the level of detection, and it's only 1 out of every 100,000 children who basically who develop AFM. But generally, they have more severe respiratory diseases, and they also associate with asthma and stuff. And so, it probably has been circulating undetected, especially since the BioFire panel has been revamped to include primers for SARS-CoV-2. So it took away a melting curve function that could distinguish 68 from the regular BioFire. And you didn't have to have a separate test. And then probably when the pandemic occurred and there were so many cases, they probably didn't go back and look to do the separate test. They probably just assumed that if you had severe respiratory disease, you just automatically had SARS-CoV-2.
So are these 168 children unusual, or are out of 100,000 people, 100,000 children, let's say, they're all exposed, how many do you think will actually get infected? And B, how many of the infections will actually go on to develop symptoms?
Well, define what a symptom is.
The thing that identified these children to begin with, it's a cold-like syndrome, right?
Right, but normally these children have very severe, like they normally, and this is what we've been battling for people to, or parents to recognize, is that these kids, it usually presents as like acute respiratory distress or asthma, so it mimics those, and it's not unique, and it's mild. Sometimes it's mild, so you might miss it.
Right.
So out of 100,000, I mean, the probability, the average is thought to be 100. 1 out of every 100,000 develops childhood paralysis.
I mean, just infection. I'm just talking about the infection rate now. Asymptomatic.
Well, I mean,
it could be asymptomatic, right?
Yeah, it's mildly. As I said, it's mostly. Sometimes it's mild, and you really have to look out for acute respiratory distress and asthma. But it's not clear, because I don't really believe in the R naught values of viruses, because they change depending on the environment that you calculate it in. So there have been papers that say like the R naught of 71 is like 15. And I'm like, okay, so you're asking how fast a kid with a runny nose can run around and contaminate everyone.
Right. So how many, have they done serosurveys? They must have done those, right?
Well, that brings us to another problem.
I see.
Which I'll be back to discuss sometime in the future. So serosurveys, yes. So serosurveys, it depends on what topic what you're also using as your sample. So like for IVIG, people have done serosurveys, and the presence of anti-enteroviruses is dependent upon where the IVIG is taken. So like it has a different composition if you do it in Europe, if you do it in Asia, if you do it in the United States. The thought, which we'll be back to discuss at a later date, right, Vincent?
Yes, Amy has a paper in review about this, Dixon.
Oh, right.
Can we come back to this topic?
Yeah, we'll come back. Yeah,
so we'll come back to this topic at a later date, hopefully before the end of the year, Dixon.
We would hope so.
That would be great.
I mean, it's under review, and then once it's accepted, it's very exciting, actually.
Yeah,
it's relevant to your question, Dixon. Yeah.
Right.
So I'm really
So these were all young kids, right? Most of them were younger than 5 years old, which is what you would expect, right?
Yeah, mm-hmm. It's the target age, it's the target season and stuff. I mean, that's the interesting thing, is that it's on the entero seasonality, periodicity, right? Whereas like RSV is completely off.
Right.
So that's the interesting thing.
So that brings up a question. So it's probably too late now to see this in the U.S., right?
Yeah, we haven't seen any 68.
So maybe next year, right?
Yeah, I think that, we might, I think next year was next year 2022? Yeah, we'll probably be back.
It's hard to know. It's actually hard to know.
I know. We'll probably be back on the even years. And to be honest, like I think she ends her paper with like this idea of a huge population of naive people, of a naive immunologically naive population. Mm-hmm. And I wouldn't be surprised if that's what we see, is that, there is this huge condition of large scale outbreaks for young children without any prior exposure or immunity to these viruses, because they've been home all this time or physically distanced.
These so it's from all over Europe, right? Belgium, Bulgaria, Czechoslovakia, Germany, Denmark, Spain, Finland, many countries. That's why there's so many authors, because the different health laboratories chipped in. In fact, it's worth pointing out that there is an organization called the European Non-Polio Enterovirus Network, NPEN, which does surveillance for what are called non-polio enteroviruses, all the other enteros except polio. And they kind of, and Heli Harvala and Thea Fisher are two of the founders of NPEN. And so I think they asked countries to, hey, tell us if you have any EVD68 in your samples.
Well, I think they're surveying for anything because 68 is not the only entero that associates with AFM.
Sure.
Like, we think of 71 primarily as endemic in Asia because it hasn't gotten a hold here or in Europe. But there's Echo 29, Echo 30, Echo B11. There's entero C99. There's a variety of enteros that are on the rise that have AFM associated.
So, Amy, they say that they first did. They took 56,000 samples and screened them by enterovirus PCR. So is that some kind of pan-entero PCR?
Yeah, it's a pan-entero. It's really hard to find specific primers to entero 68.
Right.
Because it's so well conserved.
And then they got 1,900 positives. And then out of that, they typed, the rest, 36 as EVD68. So how would you do that? Sequencing?
No, there is one pair of primers that is EVD68 specific.
Okay.
But it's not compatible if you want to multiplex and do a lot altogether.
I see. So the BioFire is a multiplexed PCR panel.
It's a multiplex PCR panel. And you don't have the opportunity to change melting temperatures and stuff in the middle.
Got it. Okay.
But here in the States, there is an FDA EUA approved primer pair, but it's just not common to use it because you can't put it through. You need a regular PCR machine, and a lot of clinical labs don't have them.
Yeah, most clinical labs do the panels, like the BioFire or some other company, right? They do lots. They do a respiratory or a gut or whatever panel,
Yeah, exactly.
Okay,
it's faster, and so one argument has always been is that you do the same thing no matter what.
Mm-hmm.
Whatever entero it is, the case management is basically all the same. I think that's been Kevin Messakar's kind of shtick for a while. He might be moving away from that now, but it was always you did the same thing. So, we recently received a bunch of enteros from clinical samples that were unknown, and some of them were classified. And our last batch of them, not a single one matched what was on the tube.
Really?
Yeah, I mean...
It had smallpox, but not vaccine?
Yeah, I mean, they were labeled like Coxsackie B1, B3, B5.
You're kidding.
No, and they're all...
using tubes.
they're all Echo 29.
Oh my God.
Which is really interesting because it's not supposed to be circulating in the United States. It's not generally associated with neurological complications. So, Ryan and Vincent and I are talking about trying to get all the stuff to make a case history paper about this and say, maybe we should expand, what we think about, right?
So
Vincent?
I want to ask you, yes, I mean, that's wonderful. I think that's a great collaboration. And Ryan reached us through TWiV, I think, right?
He was part of the U. Isn't he a friend of Dan Green's here and part of the U grant team that we tried to do?
That's right.
I think you also met him in Indiana, at some TWIM or TWiV or ASM thing or something or other.
So I wanted to ask you, is the majority of AFM associated with more severe respiratory disease? Over 50%, or is that not correct?
I don't think it's correct. I don't think there's a complete association with severe respiratory disease and the development of AFM.
Got it. All right.
So I have a couple of questions. As Vincent already pointed out, the locations of these cases geographically are pretty disparate. We've got Sweden, Iceland, France, Spain, Wales, elsewhere in the UK.
Right.
And yet we, at least according to the graph, they're all popping up at the same time. Okay. So is that like an artifact of the testing that you're talking about, or is it really lifting of? I mean, it implies to me that the virus is there percolating in the background, all over the place, and conditions change in a fashion that causes it to bloom. Is that a fair statement?
Yeah, that's what I think. I mean, yeah, I think that, as I said, the virus has been there. It's been undetectable because it's low numbers. You were home, and you know your children were not exposed in daycare centers and whatever. They weren't rubbing their their runny noses on you and other people to have it spread. But and when you came in the middle of the pandemic, the first thing that people said was, let's test for SARS-CoV-2. And if you came out positive, all your respiratory complications were said, okay, well, we have a diagnosis and that's what it is.
So, Amy, if they sequence if they sequence VP1 of these,
that's how you genotype it. Yeah.
So would you, if they gave us the phylogenetic analysis, for each country, would it fit in with whatever was circulating previously because it's percolating the whole time? It's not imported, right? It's not transported from country to country.
Well, some of it probably is. If you had relatives from Sweden who came to visit, oh my God, I can now go visit my grandparents in Italy. Yeah, I mean, some of it is. But most of it is, there's, it's, the virus evolved. So it started off as, clade A, and now it's moving to clade B1, and then it was clade D, and now it's like clade B3 seems to be the majority of viruses that you detect genetically. And what that means, I'm not really clear. Like, I don't really focus on the genetic classification. I'm more interested in, the antigenic or immune or something other than just the order of nucleotides, because I am not sure that tells us very much about the biology.
So my other question is that out of 139 cases that are reported here, 82 of them are in Wales. Do you attach any significance to that?
I do.
Okay, Vincent does.
So I had the director of the Virology clinical lab from Wales on the TWiV from the European Society for Clinical Virology meeting a couple of months ago. And the reason she was on is because Wales has one of the best diagnostic laboratories in the world. And she's on top of it. So I think they're just testing a lot and they pick up more. That's why. Yeah. That's my guess.
I mean, my guess is similar. My guess is that not all of these countries. So I heard Healy talk about this body of work in October at my monthly AFM meeting. And not all of these countries are as consistent. Some of these countries came in at the very end with a little teeth pulling. Some of them, were happy to participate. And, it's kind of, since it's passive, there's no money to do it, right?
Yep.
So, you have to kind of figure out,
Yep. Well, we will follow up on this as soon as your paper is published. We'll have you back and you can talk about that cool study, okay?
Yeah, we'll talk about other stuff. Yeah.
All right, now moving on, I thought we should do the results of a trial for an inactivated COVID vaccine because we've done mRNA, we've done adenovirus vectors. And so this is a Lancet Infectious Diseases article, Efficacy, Safety, and Lot-to-Lot Immunogenicity of an Inactivated SARS-CoV-2 Vaccine, BBV152, interim results of a randomized double-blind controlled phase 3 trial. This is the inactivated vaccines produced in India by Bharat Biotech International. And so there are many authors from India and a few other places as well. And all of this is on behalf of the COVAXIN study group. That's the official name of the vaccine, COVAXIN, which is kind of like that. I like COVAXIN. And so this is, we've not talked about this, so I thought we would do it. And Covaxin is, as we said, you grow up SARS-CoV-2. They used, actually, interestingly, the D614G variant, which arose in February, is it 2020? Yeah, I keep forgetting what year we're in.
Yeah, I have the same problem.
2021. It's
and I call next year 2020.
Series.
For some reason, I think next year is 2021. Anyway, they used that variant, but it was before any of the other variants. Just D614G. They make as someone would say, bucket loads of it.
Indeed.
They grow it up in cells in culture, and then they inactivate it with propiolactone, not formalin, but propiol, which is another option for inactivating vaccines.
Right.
And then it is mixed with an adjuvant that is an agonist of toll-like receptor 7/8. It's imidazoquinoline adsorbed to alum. And what this does is it binds to TLR 7/8 and it turns on signaling, which leads to the production of cytokines and drives inflammation, which is always good for immune responses. So that's pretty cool because remember, inactivated vaccines do not reproduce, so they are not really good at generating inflammation.
mRNA vaccines don't reproduce.
RNA vaccines do not reproduce, but they seem to be damn good at not having to need an adjuvant, right? It's interesting. Maybe it's because, I don't know. I don't want to speculate on it. Anyway, these are 2 intramuscular doses of 6 micrograms of this vaccine, of which they made a lot in India. I think it's been in over 100 million people. Where am I getting? Yes, it's been in over 100 million people, and it's been approved now by WHO for emergency use. So, and then they did this trial in volunteers. So let's look at the volunteer population. Well, first, let's look at the primary outcome. Primary outcome was efficacy in preventing symptomatic COVID, any kind of COVID, at least 14 days after the second dose, okay? So, sniffles. You had to have some symptom because that's what triggers them to send you a kit and get you tested or whatever, right? So it's got to be any kind of severity.
So they did have a subset of these individuals that they tested,
yes.
Regardless, just tested more or less at random. Okay, so
right.
we can get into this later, but one of the things that this does come up with is at least some numbers on asymptomatic infections as well.
Yeah. A secondary outcome is vaccine efficacy against severe COVID. And many people have said, well, is your severe COVID the same as mine? So they define severe COVID according to the US FDA, which requires, first of all, RT-PCR confirmed COVID with one of the following features. Clinical signs at rest indicative of severe systemic illness. That's one. Respiratory failure, evidence of shock, significant acute renal, hepatic, or neurological dysfunction, admission to an ICU, or death. Okay, that's a very clear one, right? That's severe disease. And then some of the people who, they did do RT-PCR, and some of them they genotyped to see what kind of variant they were infected with. And then they had an immunological outcome, a secondary immunological outcome, looking at the immune responses in 3 different vaccine lots, which is mentioned in the title. They wanted to see how similar the immune response was to the 3 different lots. Okay, and so they recruited 25,000 people, 25 different sites, and then they had a safety population. So some of these people, I think, ended up being positive, and so they didn't use those in the efficacy, but they used them for the safety evaluation, right? So they came in with antibodies to SARS-CoV-2, so they'd obviously been infected. You don't want those in the trial because that would mess it up, but they could use them for safety evaluation. So what they did. So 10% of the people were 60 years or older. Yeah, so a large proportion of the participants were seropositive at baseline, 30%. So they were excluded from the main analysis, but they contributed to the safety data set. So in the end, 24,000 people got 2 doses or placebo. 24,000 got 2 doses. I guess it was split among 12,000 each. Yeah. And here's what they got. 684 suspected COVID-19 cases identified at least 14 days after the second dose. 20% of those were confirmed by PCR. Some of them didn't meet the case definition, et cetera. 24 cases, 0.3%, occurred among 8,471 participants in the vaccine group and 106 among 8,500 participants in the placebo group. And that gives you an overall estimated vaccine efficacy of 77.8% against any kind of COVID. 77.8%. And then for severe COVID, they come up with 93.4%. And then, as Rich said, they have some participants where they can just do PCR randomly. The efficacy against asymptomatic was 63.6%.
Which is a pretty cool number, I think.
It is, yes. And then they have in the older participants, over 60 years of age, they have an efficacy of 66.2% for any COVID, right? That's compared to 77.8 for the overall population. So far this is good, right? These numbers are pretty good. In fact, a number of these cases, 50 of them were Delta, and against Delta, the overall vaccine efficacy was 65%, and so that is compared to 77.8%, right? And then they say in symptomatic Delta, based on CT values, the viral load in the vaccine group was significantly lower than the placebo group. How about that?
Shocking.
That's a little different from that CDC study in Provincetown, right? No cases of severe variant-related COVID were reported in the vaccine recipients. That's also interesting. So they couldn't do a analysis of severe COVID caused by Delta because it didn't cause any severe COVID in this group. How about safety? There were 15 deaths during the study, none of them considered to be related to either vaccine or placebo. And they were like cerebellar hemorrhage, stroke, ovarian cancer with metastases, sudden cardiac death, alcohol overdose, heart attack, and et cetera. And so people always say, so many deaths caused by the vaccine. They're not. They're associated. They're things that would happen otherwise. And good reactogenicity, no, let's see, mostly, the usual associated events, pain at the injection site, fever, fatigue, myalgia, less than 1%. It's all serious adverse events were unrelated to vaccine or placebo. Actually, there was one serious adverse event they say possibly related to study treatment is in one group, a case of immune thrombocytopenic purpura, 39 days after the second dose. Just one. Okay, so a good safety profile. So those are the numbers. I think. I mean, this has gone into over 100 million people. And, there are how many people in India? 1 billion?
1 billion.
Yep.
If you could make enough to put it in most of those people, it would be great. And you know what? In India, Most people get vaccinated.
Yeah.
They don't say no.
They actually talk in this paper about how they talk in one of the caveats is that this trial was in basically one ethnic population, India, and then they wanted to do it in a different population, specifically Brazil, but it was too complicated, and they didn't go into detail. Okay, but I can imagine the complications currently, given the political situation in Brazil, of pulling off a large-scale clinical trial there. A couple of other things, just these are sort of trivia, if you like, occurred to me. First of all, inactivation with propiolactone caught my attention. It's very common. It's an alkylating agent, very simple molecule alkylating agent that is its mechanism of action is supposed to be alkylating, that is, adding on carbon groups to alkyl groups to nucleic acids, and therefore inactivating nucleic acids. But it can react with other things as well. And one of the issues with any inactivating agent is, are you going to damage the antigen?
Right.
Okay. And I recall having seen some studies that suggested potentially that treatment with propiolactone might induce a conformational change to the post-fusion form, so that of the antigens, so that you would have a lot of that in the preparation. And I saw another thing about it promoting some sort of aggregation and compromising the antigenicity to some extent. But I think this is the kind of game you play with adjuvants, okay? You have to find the sweet spot between getting sufficient inactivation on the one hand and making sure that you don't trash the antigen completely on the other hand. Okay?
Wait, I'm a little confused about something that you just said. So it damages the post-fusion spike?
Well,
what you just said? But the post-fusion spike is not antigenic. That's why they put in the two prolines. So who cares?
The paper that I was referring to was one where they treated with propiolactone and then looked at the stuff under the electron microscope and saw a predominance of post-fusion spikes sticking out of the virus. And there was some suspicion that maybe the treatment was causing that conformational change, and that would compromise the antigenicity. Okay. Now, I only saw that one report. I don't think it was entirely appropriately controlled, because I don't think they had untreated virus to compare it with. So it's not clear that their purification or their preparation might have done the same thing. So I would soft pedal that one. But there was another report about propiolactone at least having some compromising effect on the antigenicity and maybe causing some level of aggregation. Nevertheless, it's clear that what they have here is safe and induces a good immune response.
Yeah, and it's protective.
In order to, I don't know that with an inactivated vaccine, you would actually be able to genetically stabilize it. Okay, you would have to create a virus that had the two proline thing in it, but I'm not sure you could grow that virus.
That's right.
Okay.
Yeah, that's right. Probably not. Yeah.
So another interesting thing is that I looked up this the adjuvant imidazoquinoline, and my first reaction to it is it's a 3-ring structure, and 2 of the rings together look for all the world like a purine of some sort. Actually look like adenine with some other garbage hanging off of it. And then there's another ring attached to the 6-ring part of the adenine. And then if you look up TLR 7 and 8, they're both sensitive to RNA. So that makes me wonder whether the mechanism isn't that this thing looks like a base.
Yeah. Right.
And that's what tweaks those receptors. But I'm totally speculating there. My other comment is that, this is a vaccine that's being produced by more traditional technology. Grow up a bunch of virus and inactivate it. And in India in particular, they are really, really good at this. All right. So this has a real advantage for them. They're all set up to make this on a large scale. They're also set up to distribute it on a large scale. It only needs to be refrigerated. It doesn't need to be frozen. So that aids in the distribution as well. And as you've already pointed out, Vincent, they don't have any problem with vaccine uptake.
We also just heard somebody who advocated that you just grow up a bunch of virus and inactivate any virus, right?
Yeah. We were at a meeting where we were proposing a novel way to make a vaccine, and someone said, just grow it up and inactivate it. The heck with that.
Yeah, call it a day.
The heck with that fancy stuff. You know, this is funny. When Salk did this with polio, Sabin made fun of him. He mocked him. He said, all he did was kitchen chemistry. But it worked, and we're using it again today, Dr. Sabin. Oh, well. They point out that their results are in line with the results for the inactivated vaccine from Sinopharm in China, 78% overall efficacy, that's good.
How's India doing with the outbreak?
I'd have to look at my, I don't know, the New York Times site. Yeah, it probably will. I'll look it up.
And while he's looking that up, they make the statement that no licensed SARS-CoV-2 vaccine has reported efficacy against asymptomatic infection in a randomized controlled trial on the basis of nucleic acid testing. So this is really good that they did that, and they got that efficacy number for asymptomatic infection. Dixon, just so to tell you something, while Rich is looking, so yesterday Daniel said we were in New York City, the number of infections are going up.
They are.
And we now have about 4,000 cases a day.
That's right.
And he said that's sort of equivalent to what we had in April of this year. But the difference is back then we had over 400 hospitalizations a day, and now we have 30.
Exactly.
And do you know why that would be, Dixon?
Well, let's see. Early diagnosis, and you can treat right away, and you can head off a lot of serious infections with monoclonal antibodies, and now we have a pill.
Oh, we are missing one big factor.
Masks.
No, vaccines.
Okay.
Those 30 people who go to the hospital are not vaccinated.
Oh, no, that's absolutely true. So in New Jersey, where we live, Vincent, over the last 28 days, there were 29 deaths altogether. So that's very low.
Probably all in unvaccinated people, right? Or mostly, I would guess.
That's right. Yeah, exactly.
Anyway, get vaccinated, wear a mask.
Distance.
Did you find the numbers in India?
I did. So, excuse me. Looking at the global map from the New York Times, the average cases per day are just short of 11,000. That is 0.8 per 100,000. The 14-day trend is decreasing in terms of their color coding. It's the sort of one of the best off places globally. If you compare that with the U.S., India had 0.8 per 100,000. In the U.S., it's 29 per 100,000.
Right.
So at least 30 times as much, and the 14-day trend is going up. So from that point of view, as a comparator, India is significantly better off than the United States, though that's kind of not a great comparator because the United States is dark red in this.
That's right. So what are the numbers in terms of India vaccinating its population?
Let's see here. I do not have. Let me see.
I think they have almost 500 million people vaccinated, but of course, they still have a ways to go.
They still have a ways to go. That's right.
We cannot throw stones.
No, we cannot. I mean, they have more people vaccinated than all of the U.S. population, right?
Yeah, but I don't care about absolute numbers. I care about percentage.
That's true.
India is reporting, according to this, 28% fully vaccinated. So they got a ways to go.
Okay.
Billion people.
I mean,
All right.
Well, 1 billion times the minimum of 2, because you need 2 doses.
That's right. That's right.
So it's like 2 billion people.
And there's also an attenuated vaccine in India, right?
I believe so, yeah.
So maybe we'll see those data. I'd be interested because we haven't talked about any attenuated vaccines. So we've got the mRNA vaccines, we have the adenovirus vectored vaccines, which we've done a couple, and now this one. And so that leaves, well, there are others, but attenuated. Novavax, the protein-based, was another kind we did. Yeah.
Yeah, but we at least learned from the meeting that we don't really like attenuated. It takes too long. Even if it's
it's true.
even if it's the best mechanism, right, of protection, we don't like it.
So Amy and I attended an NIH meeting on pandemic preparedness, and they said for each of the 7 virus families that we think are likely to lead to a pandemic, we'd like you to talk about how you would make vaccines and monoclonals, but we don't want attenuated vaccines. It take too long to make. You can't respond quickly enough.
Right.
Yeah.
Even if it's the way that you can mimic the route of infection and it gives better protection because it does everything that natural infection would do. Right.
So are children being vaccinated in India, Rich?
I do not know.
Okay.
It's a good question. I don't know either.
So here's another interesting thing you can do with this New York Times site. You could spend days here. This was my pick last week. You can look at the by country, the vaccination rates, and you can tweak it so that you can get a ranking. Like Gibraltar, greater than 99%.
How many people live in Gibraltar?
You'll expect that. And how about the monkeys of Gibraltar? Have they done that?
Spain, 80%.
Portugal has to be right up there because they have gone back. I think that they've come out and said that they're completely they feel that they've reached herd immunity or something, so that there's very few restrictions anymore.
Portugal is at 87% fully vaccinated.
Yep.
That's number 4 behind Gibraltar, UAE, and Singapore.
Wow.
Singapore, I expect to be 100%.
Yeah. What's the place, the other little island that's in the Far East that I think is also...
Sorry. Oh, no. Indonesia.
Taiwan?
Oh, Indonesia? No.
Indonesia.
There was a famous island at the very beginning of the vaccination that was ahead of everybody else.
Oh, I don't know. We got
Indonesia's not a
several
small
places
island.
here. We got the Seychelles.
Yeah, maybe that was it.
They're at 79%. Malaysia is at 78%.
So they're getting there.
What's the U.S. at, Rich?
I got to go down the list here to get to the U.S.
My finger hurts from scrolling.
United States is 59%.
And that is number what?
I don't know.
It might not change either.
It's down pretty far.
And who's the lowest?
You go down to the bottom, there are a number of countries that are not reporting.
Africa.
There are some that are kind of grayed out here. I'm not quite sure what. Chad, 0.4%.
Yeah, that's Africa.
You can't, because you probably
Yemen,
can't get into survey.
1.2%. South Sudan, 0.6%.
Yeah, maybe the numbers are really poor.
Those are places that are in high conflict right now.
Yeah, that's what I'm saying, is you can't get into survey.
Correct.
So,
Some African countries are doing better.
South Africa.
Rwanda, 20%. South Africa, 23%.
That's all?
I said you were.
I would be surprised if Kenya was not doing so. If Kenya was not doing well.
Yeah, well, they're in transition again.
Well, it's all here.
It's
all
a
very cool site. All right, now we have our last paper is all about influenza vaccines. So I think it's quite interesting, actually. This is in Cell Host and Microbe. Human influenza virus challenge identifies cellular correlates of protection for oral vaccination. First author is David McIlwain. Last author is Gary Nolan. A large group at Stanford University, University Hospital Tübingen, ARC Clinical Research, and Beth Israel in Boston. Let's see who these authors contributed equally. So that would be David McIlwain, Han Chen, and lead contact is number 12, who is David McIlwain. Okay. Don't the affiliations get more and more complicated? Anyway, as you know, right now we have a couple of different kinds of influenza vaccines. We have the traditional inactivated ones, sort of like the SARS-CoV-2 vaccine we talked about, except inactivated with formalin, not propiolactone. We have flu mist, the infectious virus produced in cells, not in eggs. We have the regular formalin made in eggs and inactivated in cells and inactivated with formalin. And then we have HA protein-based vaccines made in insect cells. But the problem is they're not great. They don't have great memory. So we're searching for something better. And the topic of this paper is a adeno5 vectored influenza vaccine, which is a tablet that you take orally and which immunizes your gut. And so it's a replication defective Ad5. It produces the hemagglutinin. It's in the pill, in the tablet that you take. There's also a toll-like receptor 3 agonist as an adjuvant. The tablets are designed to release the contents in your ileum. So they go through the stomach and they're not phased at all by the conditions in the stomach. And then they get in your ileum, which I believe is more alkaline than the stomach. And then boom, out comes the vector. It infects the mucosal cells and then delivers the hemagglutinin along with that adjuvant. It's room temperature stable and has been shown before. It's been looked at before. It does a good job at stimulating both cellular and mucosal immunity as well as serum immunity. So this could be better than an injected vaccine, right?
Yeah.
Could be, but you'd have to study it. So in this study, they wanted to know if they could identify some correlates of protection. That is, what kind of immunity associates with protection. And what they're defining as protection is actually against infection because they're measuring shedding of people. So this is a study where they have a group of people who are vaccinated with this adenovirus vectored vaccine or the traditional inactivated intramuscular flu vaccine or placebo. And then they challenge them with the 2009 H1N1 influenza virus, which is a comparatively mild virus. So I guess that's one of the reasons why they're able to do this. And also we have antivirals available in case things go awry. And then they measure shedding from the nasopharyngeal tract. And so they have, table 1 is all about shedding outcomes. So they have the individuals treated with this this adenovirus vector, 58 of them, 65% of them are non-shedders. And then the intramuscular vaccine, 59% of them are non-shedders. And then the placebo group, 35% of them are non-shedders. So in my view, this is very close. The adenovector and the intramuscular, it's a difference of 38 versus 32 non-shedders. And I just don't know what that means, right? It's not a big difference, although they're going to hang a lot of this stuff in the paper on that. They're going to look at immune cell populations in these people and say, this correlates with being a non-shedder. But boy, those numbers are pretty close. Does anyone else have a similar issue with that, or am I just looking at it wrong?
No, I agree. Those numbers are close.
Those numbers are close in a small study, but would they remain close if you did a much larger study?
That's a good point. And in fact, in the end, they do say we need to do bigger studies to validate this. Yeah. Okay. That's fair enough.
I mean, you could select your small study, Could be more homogeneous. It could be bad selectors. I don't know.
Right. So they collect the blood, peripheral blood from these individuals. And they get it before and after immunization from all these, the different the vector, the intramuscular, and the placebo. And after the before and after the challenge, and then they do the shedding and they look at symptoms as well, and they quantify virus by RT-PCR, and then they use mass cytometry to look at single cells from the peripheral blood of these people and say, what kind of cells are they? And this is very cool.
This is the coolest part of the paper, which makes me want to go and do this for our stuff.
Mass cytometry, you use antibodies tagged with metal because you're going to do mass spec on it, right?
Yeah.
Basically. Instead of, you would normally take an antibody and conjugate it to a fluorophore, and then you put that through the flow cytometer.
Yeah, but then you have to do all this canceling out and recalibration. Yeah. That's very complicated.
Plus you're limited, right? You're limited to how many different colors you can do.
Well, yeah, but there's always bleed through in the channels.
There's bleed through, that's right.
It's not always the cleanest experiment.
I just pasted an image into the show notes that shows the technique and also shows how you get these nice sharp peaks with the metal mass.
I mean, it's amazing.
You don't get any overlap of the spectra, so you get really much better resolution that essentially allows you to use many more markers. Mm-hmm. Okay, so what they say up to 40 or even more.
Even more. And the difference also is the amount of cells that you can look at all at once. Like you can do this with millions of cells, whereas flow, you can only do like a couple thousands.
Well, I think in flow, you could certainly sort millions, but they say, I don't know. They say unlike single cell sequencing, you can look at millions rather than thousands of cells per sample.
Yeah. So we're going to go from LibreSeq to this, Vincent, just to warn you.
I think this is brilliant. The different metals on. Oh man, it's so cool. Anyway,
it is.
So they say first of all, this adenovectored vaccine, which is called VXA A1.1, VXA we'll call it for short, offered more protection against shedding than the inactivated influenza vaccine. We've already discussed our problems with that. However, here's the cool thing. The antibodies induced by the adenovirus vector were lower than for the intramuscular. And they measured hemagglutination inhibition antibodies and bona fide neutralizing antibodies. Okay. And they were lower compared with the injected vaccine, but there was less shedding with the adenovirus vector. So they say this suggests that maybe cellular responses are important for this. So that's the focus of that. So they do their mass cytometry to whole blood samples. They have a 43 antibody panel because, the immune system has all these cells with different markers and different functions. And so they have to all be sorted out. And that's how they do it with this here. And they also have an HA probe. So for this single cell, they have a hemagglutinins because they want to measure cells that bind the hemagglutinins, right? The B cells. But this hemagglutinins is changed so it doesn't bind sialic acid. So that lowers the background. It's very clever, right? They change one amino acid in the sialic acid binding site. So this will not stick to everything and give you a lot of background. It will just stick to the antibodies that recognize it.
So I just to be absolutely clear here for the uninitiated, you take the blood, you react it with this panel of 40-ish antibodies, each of which are a different color, okay? And so any given cell, depending on its characteristics, may have a number of different antibodies bound to it. Right. And when you stick this sample through the machine, it can look at this one cell at a time and ask what antibodies are stuck to it.
Right.
It can be 1, can be 5, can be 10, or whatever. And then based on that profile, tell you something about the identity of that cell. Unbelievable.
And so just to be clear about this HA, so they are, instead of using an antibody to stain cells, which is done for most of this, they're using HA to stain, and the HA is conjugated to a metal, just like the other stuff. But the idea is that the HA will bind antibody on the surface of what are called plasmablasts, which is between a naive B cell, right, and a plasma cell, which is the one that makes a lot of antibodies. Right, so when a naive B cell sees antigen, it becomes a plasmablast, and then a mature plasma cell. So they want to pick up the plasmablasts. They have on their surface the antibody that they're specific for, and so they want to see HA bind that. Okay, and so they change the HA so it wouldn't stick to all sialic acid, which would give you an impossible signal. Right. All right. So these markers can pick up, the typical cells, B cells, T cells, NK cells, monocytes, dendritic cells. And then, of course, they can do way more than that. They can look at all different kinds of subsets with different markers on their surfaces. And they have these plots where they can make these two-dimensional pictures of all these different kinds of cells. And I've seen these before in some of the seminars in our department. So I don't want to go into the individual cell populations, but rather give you the overall picture here. So they found, first of all, what they say plasmablasts, cells with plasmablast features. There's certain markers on their surface that had differences between shedders versus non-shedders. They saw clear differences, right? And you have to understand that there's a lot of modeling going on in this study. It's not just data collection, but then they do modeling and use the results of the modeling to make their conclusions. I guess no human could just look at the data and say, yeah, it's 50 versus 10%, right? So they have to do a lot of that.
It's a lot closer than that.
Yeah, it's very close.
Which gives them the modeling and the principal component analysis gives them the ability to do statistics, right? And then say it's statistically significant. Because if you and I looked at it, we'd be like, who cares?
Yeah, right. So basically, there are all kinds of plasmablasts with different markers on their surface, but each of these correlated with protection from shedding in the adenovirus group, but not the inactivated group or the placebo group. Okay, so their numbers were higher in the adenovector, and it correlated with less shedding, and it didn't correlate in the other. So they're thinking, okay, these are important cells for reducing shedding, and they're making antibodies, right? So that's a plasmablast. That's what it does. And they also identify a marker. So this is hard to do. This is not something that you would do clinically, right? This is too hard. But they do identify some marker that is associated with protection against shedding. And they say this correlate may be cheaply and easily quantifiable in future studies with the use of a small fluorescent antibody panel. So that, this is too complicated to use in a clinical setting, but maybe they could take the results and use it. All right, so some kinds of plasmablasts associate with protection. And then they have what they call a cluster of T cells with CD4 positive memory features, right? With all kinds of markers that I don't want to tell you because it'll just confuse you. But they think that these have been induced by vaccination. And some of these, in fact, have markers that are associated with mucosal homing. So there are actually some surface markers on these memory T cells that are associated with going to mucosal surfaces, which of course is where you want them to have a memory response to a respiratory infection, right? And again, these seem to correlate with protection afforded by this adenovirus vectored vaccine. Now, However, it's not statistically significant. So there are different kinds of memory T cells. There's central memory, there are effectors, right? And the effectors are the ones that are doing the work. The memory are kind of memory T cells. And they said there's some differences between the two different vaccine kinds, but it's not significant. It's not statistically significant, even though it looks like it's leaning towards the adenovirus vector. Okay. And then there's another kind of model they apply to these data, which I really like the name of, and I probably can't understand how it works, but it's called random forest modeling. Isn't that a great name? And it must be related to how it works. But they basically conclude that there's a more importance for cellular immune responses for protection against shedding with the adeno vaccine compared to the injected vaccines. And they can identify a number of cell subsets, T cell subsets that seem to be correlating with this. I guess the idea of a random forest is that you have all these trees, right? And you can figure out if there are associations between them or something like that.
Right. What they didn't do, I guess, is to test both together to see if there's a synergism between injection and the oral vaccine.
No, they didn't do that, yeah.
But that would be interesting to see, wouldn't it?
It would be, yeah. It would be interesting. Maybe you could get the best of both, right?
I mean, you take a pill and you get injected at the same time and voila. Sounds easy.
Yeah.
Probably isn't.
So it's been known for some time that a correlative protection for the inactivated influenza vaccines are what are known as the hemagglutination inhibition titer, right? It's the amount of antibody that inhibits hemagglutination, which is the ability of virus to stick to its receptor on red blood cells. So that's been studied for many years, and it's a great correlative protection. But they noticed here that it didn't correlate with protection against shedding by this adenovirus vectored vaccine, right? Which seems to be correlating more with cellular immunity. Plasmablasts, of course, make antibody, but hemagglutinating inhibition antibodies don't seem to be correlating with protection. So I don't know what the plasmablast data mean, actually, but I find that interesting.
So, Vincent, can you have two separate groups? They're both protected, but in one group they shed, and then the other group they don't. So this has got a herd immunity kind of an effect that you're looking for. But the question is, do you have two separate groups, or do you have a subset of the one group? They're both protected, but in one they shed, and then the other one they don't. Because in the injected group, that's what everybody's been getting for ever, right? And so we assume some protection. And
well, I think that the table shows that there is some inhibition of shedding with the traditional injected vaccine, right?
Right, but
it just seems to be less than this adenovirus vector vaccine.
Well,
right?
we just said at the beginning it was marginally less.
Yeah,
right?
It's marginally better, but
right.
But there clearly is some protection from an intramuscular inactivated vaccine.
Oh, yeah.
But these data show that the kinds of immune responses that correlate with that protection are really cellular, as opposed to the inactivated.
So what it says is the way you administer the vaccine is defining whether or not you're going for antibodies or whether or not you're going towards T cells. Which isn't very surprising because we discussed this when you and I did a TWiV, just you and I.
I think that these mucosal targeted vectors make sense that they're going to, in fact, induce some kind of immune response that's targeting the mucosa, and they find these cells. These cells with mucosal homing properties based on a specific surface protein, and they say this could be a correlative protection along with the plasmablast, and we need to just look at more people to make sure that that's the case, right?
Well, I also think the other message is that we've underappreciated. I think that in the paper somewhere they say something about OPV.
Yes.
And stuff. And I think that, we've lumped things all together, right?
Yeah, for sure.
Guts and the respiratory tracts and mucosal surfaces and non-mucosal surfaces. I don't think we've really fully appreciated the subtle differences of the cells and the mechanism and the structure of each tissue and how it defines pathogenesis and how effective or what is the effective component of the immune response.
Right.
So to give you the polio reference, so this
Exactly.
cell surface protein is called alpha 4 beta 7, okay? And this identifies CD4 cells with mucosal homing properties.
Yes.
And they say their data aligned well with the association between oral polio vaccine elicited alpha 4 beta 7.
What I was going to ask you about that, actually.
Circulating antibody secreting cells and protection from poliovirus. So they find plasmablasts and alpha V beta 7 are correlated. And the same thing is for polio, right? There's a 2016 study that Amy referred to. And in fact, here's the real conclusion. Our results are consistent with the notion that circulating antibody responses are more relevant for protection conferred by the intramuscular inoculation, whereas circulating cellular responses are more relevant for the protection conferred by the adenovectored mucosal delivered vaccine.
Right.
So the thing is, maybe the differences in shedding are not that great, but here you have a vector that seems to preferentially target the mucosa. So that could be better in the long run, especially if these memory cells stick around, right?
Well, it's better if you take into account Rafi's data, right? That said the injectable gave a really bad T cell response, right? Isn't that what Rafi's paper did say and stuff? And then if you look at Marion's work, when we were writing the grant and the papers and stuff, and I think you even put it in your TWiV possible folder where she says, IPV really sucks at making a mucosal response on this, and you really need exposure to the natural route of infection, right? I mean, that's kind of like the paper that should have been done before this, right?
And that's what this is, right? This is it's not the right mucosal surface, but it's a mucosal surface.
It's closer.
It's closer.
It's closer. It's closer, right?
Yeah, for sure.
So, I mean, and when we were talking about Marion's paper.
This is Marion Koopmans, by the way, folks.
Yeah.
It's a little inside baseball,
Oh, sorry.
People don't know Marion, but that's fine.
Well, this was a conversation you and I had when I must have been stressed out about some grant that we recently...
Yeah, but nobody knows what you and I are talking about. That's the thing.
Yeah, well, it's a good thing. Sometimes it's a good thing that they don't sit here all day long and listen to us. Now I forgot. Okay, never mind. Move on.
No, the polio story is, and it's correct. They're similar, and Marion Koopmans did that work quite a few years ago, right?
Right, and it's been ignored or it's been forgotten.
Well, I think the polio community
that's involved in
vaccination. Yes, not the broader polio community. I don't think there's a broader polio community anymore, right?
Let's just put it to you this way. In some of our other meetings with other polio virologists, I didn't get that they appreciated those subtleties because that's not what some of them said to us when we were at the NIH meeting.
Okay, so one last thing about this paper. They say, so these correlates, so the plasmablasts and the mucosal homing CD4 T cells, they can be measured in blood 7 days after vaccination, whereas it takes at least 4 weeks to measure antibodies in the blood that are hemagglutination inhibition. So it's a rapid, you could really quickly evaluate if a vaccine is working or not, right? That's cool. I like that.
So I got a couple thoughts. First of all, my assumption is that they're measuring shedding just as sort of the best and most convenient and most consistent indicator they have as to whether or not somebody's getting infected. Okay. They're not, might be too complicated or, not very sensitive to look for symptomatic infection or anything like that. Shedding is going to be the easiest thing. So I don't know how that translates to in a real life situation what the protection would be, but it's the best indicator they've got. Second, I would have liked to see a comparison with flu mist. Because flu mist, I think one of the potential. Okay, so flu mist is the live attenuated virus that you actually put in your nose. Okay, so that ought to give you, that's a mucosal immunization.
Right.
So I'd be very interested to see what the profile in these experiments looked like with flu mist.
Yes, absolutely. That's a great point. Yeah, because that would be, because flu mist isn't great, right, in terms of protection.
No, it's about the same as the intramuscular guys, I think.
So I wonder if you'd see a difference in these cellular responses or not. Yeah, that's a good point.
So the other thing I keep thinking of, and here I'm skating on my typically thin immunology ice, okay, is that do I understand correctly that various compartments of mucosa are functionally connected? Okay, so that, I mean, the implication of this is that an immunization in the gut mucosa could give you an immune response in the respiratory mucosa. Okay?
That's right. That's right.
Yeah.
And I'm thinking that, and I think that's pretty well understood, right?
Yeah.
And I'm just trying to put it together. I'm thinking in order to measure this, they're measuring blood. Okay. And the protein that we've talked about that you've called a homing protein is an integrin, which we talked about before.
Exactly.
So basically you're immunizing in the gut. You're getting a response that represents a mucosal type immune response, and that's spilling into the blood and circulating around. And because it has they're got mucosa specific integrins on it, it's targeting remote mucosa, presumably, okay, and giving you immunity in your respiratory mucosa.
Yeah, but I don't think that's uncommon. I mean, the guy here, there's a parasite guy, right, Vincent, here, who stays, what is it, IC3 cells in the gut that go into the respiratory tract? Do you know who I'm talking about?
Yeah. Yeah, the guy who came from NIH who studies the mouse model. Yeah.
There's a lot of Helminths that do that also.
Yeah. It's a Helminth model. Yeah.
Yeah. And that's what I'm saying. So it's not,
That's right.
I think
not
that's
unusual.
correct. Yeah.
That includes the urogenital tract also, by the way.
Yep.
I also think that it occurs to me that adenovirus is a particularly appropriate vector for this, because adenoviruses, I don't know exactly Ad5, but adenoviruses generally infect mucosal tissues, both gut and respiratory epithelium mucosa. And there's also some other history here. I think I may have closed that down. Yes. A way back history. I think we've talked about this at some point or another. There is an adenovirus vaccine that's used in the military for a respiratory infection with adenovirus type 4 and 7. Okay. And that's really interesting because these are adenovirus infections that cause a respiratory symptoms. And when you get a bunch of immunologically naive young bucks together in barracks and crowded conditions, they pass this around, and it causes a problem in military recruits. And so the vaccine that they've created is actually the wild type adenovirus type 4 and wild type adenovirus type 7, formulated into a pill that I imagine is much like this, that these guys take, and they get infected in their guts, and these viruses don't cause symptoms through that route of infection. But the immunity that they get, because of what we've talked about, there being sort of spread of this immunity to distal mucosa, gives them immunity to the respiratory infection. So there's a history here of using adenoviruses in a tablet formulation to immunize through a GI route.
So you might be interested to know how this vaccine protects against challenge in terms of symptomatic. Let's see. So there was a 2020 paper looking at this. That was the first publication of this challenge study with this adeno-vectored vaccine. And so they say influenza positive illness after challenge was detected in 29% of individuals in the adeno-vectored vaccine group, 35% of individuals in the intramuscularly inactivated vaccine group, and 48% in the placebo group. So the adenovector did a little better at protecting against illness than the intramuscular, and then both did better than the placebo. So again, I think that would be interesting to see in a larger trial, right? This is a phase 2, so it's a small trial. So I think we'll see more different influenza vaccines in the future for sure, right?
Pretty cool. I wonder how much a mass cytometer costs.
Let's see, how much?
It's got to be millions. It's probably millions of dollars.
Millions? Who could afford that then?
Probably buy it on eBay, right?
Yeah,
you do it as a group.
Yeah, you have
it says,
to do it.
well, if it's made by Agilent, one of them is made by Agilent, and the headline on the page is "Powerful yet affordable."
Oh, I was wrong.
That. Sounds like a Tesla.
And you know what? They're not going to tell you on the website.
You got to write them and get a quote.
I got to fill out a form and get a quote, and then they'll bother me for the next 5 years.
Right. It's probably the metals that are expensive.
Yes, I'll bet that's it.
Well, mass spectrometry used to be I remember as a graduate student, there was a guy who did mass spectrometry, and his spectrometer took up a whole room.
That's right.
Okay.
That's right.
And now it's a box,
Yeah, computers were like that too, Rich. So, you know.
How much is a mass spec nowadays?
I don't know.
Look up MALDI-TOF.
Yeah, but they won't tell me how much it is.
Somebody will write in and tell us.
But they're small now, right?
Yeah.
They're much smaller than
They're on the bench top.
That's right.
Oh, and they have them in clinical microlabs, right?
Yeah, the MALDI-TOF.
Exactly.
MALDI-TOF, that's right. Okay. All right. Time for some picks, and I can't wait to hear what Dixon's next comedian is.
Well,
you don't even like comedy.
Vincent, it's a comedian that I think you're familiar with. His name is Rodney Dangerfield. And Rodney Dangerfield has a checkered past in terms of eliciting humor with stand-up. He's one of the quintessential stand-up comics, like Henny Youngman, and it goes way back to the Jewish comedians that used to go up to the Catskills and the Borscht Belt, as it was called. Rodney Dangerfield grew out of that genre, but he's more urbane and he's self-deprecating, obviously. So his main shtick is that no one gives him any respect. And he always talks about, I don't get no respect, I don't get no. And then he's usually saying that on the Johnny Carson show. And I think this YouTube version is the one I have with him on the Johnny Carson show. He'll say things like, they're slightly off color, but it allows you to fill in the gaps. So he'll say like, I had to go out. I wanted to go out one night and find out where the action was. So I got in a cab and I asked the cab driver to take me where the action was. He took me back to my house. That sort of thing. I'll never forget, he lives in such a tough neighborhood. My tough neighborhood, and Johnny Carson said, well, how tough was it? He says, my neighborhood was so tough. He says, when you pour cement and you make sidewalks and you put your hand to make a handprint on the sidewalk? He says, well, in my neighborhood, when you put your hand on the sidewalk to make a print, you felt another hand. So, he says the obvious in such a wonderful way, and of course his big movie was Caddyshack, and I love him, even though he isn't always funny. I think he can routinely make me laugh simply by his bulging eyes and the way he adjusts his tie. His whole comic impression of a person that's in trouble, no matter what, is an appreciated genre of comedy that I pick in my top 10.
His original name was Jacob Cohen.
Exactly. He could have been a Borchfeld comedian.
And this is very funny. So his first wife was Joan Child, who he divorced in 2004. And then actually, he had a different wife first. Joyce Indig he married from 1963 to 1970. And then he married, what is this? I don't even understand. He had 3 wives, but 2 of them were the same. So he must have gone from one to the other back.
He remarried the same
It's
woman.
really funny.
Right. That's right.
And he was born in Deer Park, New York, which is Queens, right?
Yeah.
So when I was a kid, I used to like Rodney Dangerfield because of the bulging eyes and how he'd always adjust his tie and move his neck around like that. There was a real shtick.
All of that.
Yeah, I don't get no respect.
Nope. Never did.
Thank you, Dixon. That's number 8 or 9? Where do you at?
I think that's 8. I've got 2 more.
Cool. 2 more. All right. Amy, what do you have for us?
Calder at MoMA, so the
great.
Museum of Modern Art. So I like his balance and his abstractness and his love of the sea and stuff. And, I've always wanted to have a Calder mobile of viruses hanging over my desk. But it's just that he really appreciated the elemental systems that animated life and stuff. So,
Amy, have you been to the National Museum down in Washington, D.C.?
I have, and the Hirshhorn Gardens too.
There is an enormous Calder hanging in the National Museum.
Yeah.
And it's so sensitive that you can actually blow on it and get it to move.
Yeah. And, right outside in Chicago, outside of, what's the park that I'm thinking about? Like down south on Miracle Mile on Michigan Avenue, there's a big Calder, a big red Calder.
Yeah, no, he's marvelous. He's absolutely marvelous.
Yeah, and I loved going to Storm King as a young adult and walking through the Calders.
That's right.
And just his sense of balance, like with him and Sarah and David Smith and stuff.
Is this a permanent display?
No, it's actually, it closes in February.
Didn't they have a big Alexander Calder at the Whitney about 5 years ago, I thought? And one of his early constructions was of the circus.
Yeah. His earliest constructions were small mobiles.
That's right.
Then he expanded out into industrial-sized art and sculpture. And like this stuff at Storm King that you associate with him, and the big red sculpture in Chicago and stuff. Yeah.
So was he the first to make mobiles into art?
Probably.
He's one of the first. Yeah. Go ahead.
He has mobiles, and he has stuff on the ground, big metal things, right?
Yeah.
He has a lot of different kinds of art.
Yeah. But actually, one time when my friend from college was here and he went to see a Calder exhibit, I was stuck in the lab. But they made him take off his shoes and stuff so that they didn't get dust. Yeah, because the dust and stuff was going to influence the way it hung and stuff.
Oh, my.
Calder.
Cool.
The name of the exhibit at MoMA is Modern from the Start. So apparently he started doing this in the 30s. I mean,
he was like a Bauhaus. He was like an early Bauhaus.
Exactly.
Which is an era that I really like.
Yep, me too.
And I'm surprised that you're not a bigger fan, Vincent, of Calder, because it's an era that you like, Bauhaus and Gropius and stuff.
Maybe I underappreciate Calder. He's really good. Yeah. Rich, what do you have for us?
So I have an article from an online sort of popular science publication called Science Alert that my wife brought to my attention, entitled "Useless Specks of Dust," end quote, turn out to be building blocks of all vertebrate genomes. And I also have, for those who want to dive in a little deeper, the original paper, that PNAS paper that this is reporting on. And this was news to me. It turns out that reptiles and birds, if you do try and do a karyotype, that is, look at the mitotic chromosomes, okay, have, the regular sort of big old chromosomes that you're used to seeing, and then all these little bitty things, okay, that when people first saw them decades ago, thought, oh, I just got dust on my slide or something like that. Then people over time look a little closer at them, and it turns out that there's a whole slug of what they call microchromosomes, right? And in this particular paper, they compare all of these microchromosomes and come to the conclusion that a lot of these creatures have a lot of these microchromosomes very much in common, okay? And we're talking birds and reptiles of one sort or another. Not only that, but they're in common with, I'm going to kind of blow it here with the name of this, an ancient creature from 684 million years ago called Amphioxus.
Okay? Amphioxus? Oh, yeah.
Yeah.
And so the idea is that these microchromosomes are, in fact, a signature of a very, very old genotype, if you like, that's been preserved throughout, to varying extents throughout birds and reptiles. And then if you look at more recent creatures, mammals and et cetera, interestingly, you find that the same sequences are in the larger chromosomes. Okay. So basically, the large chromosomes have sucked up these microchromosomes so that they're all in the large chromosomes now. Really, really interesting. And they have some speculation in the paper as to
That's not a pun, is it?
What works better. Okay. Having a bunch of microchromosomes or having the large chromosomes, and they come down in favor of microchromosomes, that maybe sucking these all up into the larger chromosomes isn't necessarily have a great evolutionary advantage. The other little interesting tidbit is that when you do the chromosome squash on these, you find, and even when you develop appropriate tags and do tagging fluorescence in situ hybridization on interphase DNA, that is not in mitosis, you find that these microchromosomes cluster in specific locations in the nucleus. In a chromosome squash, they're all clustered in the middle, and you can find particular clusters in interphase chromosomes. At any rate, I thought that was pretty interesting.
I didn't know this.
No, it was news to me. That's why we picked it out.
It's a PNAS paper.
Yeah.
Wow. Microchromosomes are building blocks of bird, reptile, and mammal chromosomes. Very cool. Useless specks of dust.
And they got some cool pictures.
Yeah.
Rich, can you speculate with specs?
And it looks like, because I'm accessing it here on my computer that's not privileged, it looks like the PNAS paper is open access.
Cool. All right. So, Dixon, I am now on Seminal Papers in Molecular Biology, number 9. I'm almost done.
Number 9.
I just have one more. I have to pick one more next week. Boy, that's going to be a tough one.
Whew.
But for today, we have, this was a hard one, a second paper by Watson and Crick.
Dear.
Published in Nature in 1956, 3 years after the DNA structure paper. And this is called Structure of Small Viruses. And this is something that a lot of people don't realize that Watson and Crick did. They actually set forth the principles for how at least viruses, or as they say, viruses which have a fixed size and shape are built. Because the last sentence of the paper is, we believe this hypothesis is likely to apply in this form or a simple variant of it to all smaller viruses which have a fixed size and shape. Can you still publish hypotheses in Nature?
Better be a good one.
Better be a good one. Anyway, so what they did here is they noticed that they say almost all small viruses are either rods or spheres. So that's what we knew back then from having watched them under the electron microscope. And so they try to come up with an explanation for that, which they put together by looking at the structures of the known rod-like and spherical viruses, rod-like like tobacco mosaic virus,
right? TMV.
Or spherical like poliovirus, and many others. And they said that basically the rod-like viruses, they're all made of a few proteins repeated many times. So the tobacco mosaic virus has an RNA genome with one protein coding it, and it's a single protein repeated many, many times coding the RNA.
Right.
And they knew this from studies that had looked at the protein composition of these viruses, and they said, oh, there are not that many proteins here. So they said that the rod-shaped viruses are built with what's called helical symmetry. A single protein interacts with the genome and with other single proteins and coils around to form that rod-shaped virus. And so now we know that many viruses have helical nucleocapsids when they're inside an envelope. So tobacco mosaic virus is a naked nucleocapsid, but influenza virus, SARS-CoV-2 paramyxos, they have helical genomes bound to proteins, same principle. And then the spherical viruses, they said these are built with some kind of symmetry that takes one or a few proteins and repeats it many times. And so this was the founding hypothesis that was used by a number of structural biologists, including Casper and Klug, who are structural biologists and who found that these spherical viruses actually have cubic symmetry, and it turns out that they're built with icosahedral symmetry. So I think this is a really important concept that led us to understand these two important structural groups of viruses and how they're built and so forth. Nowadays, we know, of course, that there are many viruses that are different, like the pox viruses are all different. They don't follow any of these rules. The giant viruses are quite different, but certainly for the small ones with fixed size and shape, this is how they're built. And so they didn't just study DNA. They also made a contribution to virus structure. I think that's cool.
Do they have any suggestion that the spherical ones would have icosahedral symmetry?
Let's see. That's a good question.
I think that if you're going to build a container using a single subunit over and over again,
right?
That icosahedral symmetry is about the simplest way to do it.
Yeah, I think that was Casper and Klug subsequently who figured that out.
They talk about three possible cubic point groups as spherical viruses: tetrahedron, cube octahedron, dodecahedron, and icosahedron. So no,
right.
They didn't. Icosahedron was one of their possibilities. Interesting.
So they basically said for these spherical viruses, our hypothesis is that the shells are constructed from a large number of identical proteins packed together in a regular manner.
Right.
So that is all they went, and then Casper and Klug went into the icosahedral and all the variants of that.
And introduced the quasi-equivalent thing that says
exactly
it's not exactly all the same contact.
Yes,
you got to cheat a little bit, right?
Yes, when you get above 60 subunits of the same protein, anything more than 60, then you have to have quasi-equivalents because they're not quite the same in the same environments. That's right. So I just, from teaching virology, I always mention this work, and I think it is very important, and maybe not so many people appreciate it. So that's it.
Well, I think
I don't know.
nowadays
They came up with the 2-fold, 3-fold, and 5-fold axes.
Yeah. Oh, in this paper?
Yeah. It's on page 474. They say each of these 3 classes must contain at least 4 3-fold axes, 3 2-fold axes arranged as for a tetrahedron. The first class contains no additional axes, while the second and third have 4 and 5-fold axes respectively. This arrangement of symmetry elements is known as the point group, in contrast to the space group, which applies to a regular arrangement extending into infinity.
Yep.
So I don't know. They're pretty close.
Yeah.
Yeah, they are close. And they say towards the end, it is not easy to explain in a short space why there are so few ways of building a spherical shell. But the reader can soon convince himself that it is difficult by trying to draw identical shapes which completely cover the surface of a tennis ball. It's impossible, for example, to do this entirely with hexagons, even if their shape is irregular.
Yeah, but they say up above from the paragraph that I just quoted from, notice that in all these point groups, the minimum number of asymmetric units must be a multiple of 12. 60 is a multiple of 12.
That's right.
5 times 6.
That's right.
It's 12.
Yeah, that's the regular polyhedra. That's right. Yep.
So,
yeah, so they got most of it.
They're pretty, they're like
pretty good.
95% of the way there.
We have 2 listener picks. One is from Charles, who sends a link to a cartoon on iFunny, which is labeled social media. There are 2 people looking, they're at a fence, and on the other side of the fence, there's a water tank which is leaking. And the guy looking through a hole in the fence is labeled social media, and he's saying, "It's raining. You lied to me. I can see it all from here." And the scientist, of course, is on a ladder looking at the water coming out. He probably said, "There's water leaking out of a tank." And the other guy said, "No, it's raining. I can see it. You lied to me." And that's what social media is all about. Yeah.
Pretty good.
I think it's great. And then Dave sends us a link. Thought the above article while listening to episode 812, during which Rich talked about designing templates for future studies, which can be agreed upon by international groups. And he sends a link to an article by Jenny Blair in PitMed called A Whole New Ball Game. And it's all about designing trials, the way you structure a clinical trial and how that's changed over the years. And so nice figure that illustrates that as well. 37F3C in Pittsburgh, just a recently retired radiologist, Dave. That'll do it for TWiV 832. Show notes at microbe.tv/TWiV. Send your questions and comments, twiv@microbe.tv. If you'd like to contribute and have your contribution doubled, go to parasiteswithoutborders.com and click the donate button. Dixon Despommier, Trichinella.org, thelivingliver.com. Thank you, Dixon.
Pleasure.
Always good to see you. We're going to see you next week on Saturday to help clean out your office, right?
Yeah, you have to wait. I'm going to wait for you on the outer steps so that we can go in together.
I'll be here too.
I have to get you in, right, Dixon?
You do. You have to get me in.
Will I be able to do that?
Sure.
You'll be my guest.
I'll be your guest.
Okay.
Well, if not, since I'll be here, you can both be my guest.
Well, if you were there ahead of me and you don't want to wait, we can tell Amy to come get you.
I'm going to be down there at 10 o'clock, so that's the time we're going to get there.
I'm here way before that, Dixon.
Oh, yes, I know that.
Amy Rosenfeld is at Columbia University Irving Medical Center. You can find out what she's doing these days at enterovirus.net. Thank you, Amy.
Thank you.
Rich Condit, Emeritus Professor, University of Florida, Gainesville, currently in Austin, Texas. Thank you, Rich.
Sure enough. Always a good time.
I'm Vincent Racaniello. You can find me at virology.ws. I'd like to thank the American Society for Virology and the American Society for Microbiology for their support of TWiV, and Ronald Jenkins for the music. You've been listening to This Week in Virology. Thanks for joining us. We'll be back next week. another TWiV is viral.